In this section, we're going to look at mechanical energy. So far, we've seen two kinds of energies: kinetic energy, which is motion energy, and potential energy is stored energy, that is energy that has the capacity to be converted to motion energy. What we call mechanical energy is the sum of kinetic energy and potential energy. This is the sum of kinetic energy and potential energy. So we're going to use ME for mechanical energy. So you can say that mechanical energy equals kinetic energy plus potential energy. Okay, as you've seen before, kinetic energy is always half times mass times speed squared, and the form of potential energy depends on the type of force. For example, you've seen that if the force is gravitational potential energy, that is mg times the y coordinate. If the force is the force due to spring, it's half k times extension or compression squared, and so on. Okay, so this is the formula for mechanical energy. It's the sum of kinetic energy and potential energy. So we have the following formula. This equals half mv squared, which is kinetic energy, plus u, which is potential energy. Now let's write the expression for mechanical energy for gravitational force. For gravitational force, we've seen that the gravitational potential energy with respect to y equals 0 is given by the formula mgy. Maybe just let's say g over here. This is the gravitational potential energy, mgy. So the mechanical energy would be half mv squared plus mgy. So if the force involved is gravity, this is a form of mechanical energy. And for the force due to a spring, for the force due to a spring or elastic force, we've seen that the potential energy is half times the Hooke's constant, the spring, and then times extension or compression squared. Okay, so the form for the mechanical energy of a spring would be half mass times speed squared plus half k times extension or compression of the spring squared. Okay, now if both gravity and the force due to spring are involved, then of course the potential energy would be the sum of gravitational potential energy and elastic potential energy. So let's say if both gravity and the force due to a spring are involved, then of course the potential energy would be the sum of gravitational potential energy plus the elastic potential energy. Okay, so in that case, the mechanical energy would be the kinetic energy, which is half mv squared, plus gravitational potential energy plus the elastic potential energy, or the energy stored by a spring. Okay, now let's consider an example of calculation of mechanical energy. Example, let's say we have an object on a 10-meter tall building, okay, and let's say its mass is 2 kilograms. Okay, let's say thrown with a speed of let's say 10 meters per second. Okay, so the question is A, calculate its mechanical energy, let's say with respect to the ground. With respect to the ground, what that means is we put the zero of our coordinate system at the ground. Okay, so we're going to use this coordinate system over here because we're told with respect to the ground. So this is the y equals 0 line, and so it follows that in this case our y is simply the height of the building. Okay, this would be y, so that would be 10 meters in this case if we put our origin over here. Okay, and so we have the speed is 10 meters per second, v is 10 meters per second. We're given the mass is 2 kilograms, and the y with respect to a coordinate system whose origin is the ground is 10 meters. Okay, so the mechanical energy would be half m speed squared plus mass times gravity times y. Okay, it would be half times 2 times the speed squared plus 2 times gravity approximately 10 and the height or y coordinate 10. So this is 100 plus 200, 300 joules. Okay, now let's change the location of the origin of the coordinate system. Let's ask the following question. B, calculate the mechanical energy of the object, let's say with respect to a point 2 meters below the top of the building. So now you see our origin has changed. We're talking about calculating the mechanical energy with respect to a point 2 meters below the top of the building. Okay, so now we're going to another coordinate system. Okay, a coordinate system whose y equals 0 is over here. Okay, so according to this coordinate system, our y is 2 because we're told to calculate the mechanical energy with respect to a point which is 2 meters below the top of the building. So for this particular problem, we put our origin over here, and this is going to be our height. So y is 2 in this case. Okay, so in this case, y equals 2 meters. All right, and so the mechanical energy will change. Half m v squared plus m gy. So in this case, you see half times 2 times 10 squared plus 10 times 10 times 2. Okay, so you've got 100 plus 40. So you see, gravitational potential energy does not have a unique value. It depends on where you put your coordinate system. All right, the change does not depend. The change in potential energy does not depend on where you put your coordinate system, but the potential energy itself depends on where you put your coordinate system. Okay, so we'll have different mechanical energy depending on where you put your coordinate system. Now we're going to look at the principle of conservation of mechanical energy. Principle of conservation of mechanical energy for conservative forces. Mechanical energy for conservative forces. Okay, so first I'm going to state the principle, and then we're going to prove it. Okay, so this principle says that if all the forces acting on object with zero contribution to the work done are conservative, then mechanical energy is conserved. This law says that if all the forces with non-zero contribution to the work done are conservative, then mechanical energy is conserved. Mechanical energy is conserved. Okay, so this law states that if all the forces that do not contribute to the work done acting on objects are conservative, then the mechanical energy at the initial point will be equal to mechanical energy at the final point. Okay, so let's try to prove this principle. Now, if you remember the work kinetic energy theorem, kinetic energy theorem, that theorem states that the net work done on object equals the change in kinetic energy. Okay, but if all the forces with non-zero contribution to the work done are conservative, then this also equals work done by the conservative forces. Okay, so you can say that the work done by the conservative forces equals to the change in kinetic energy if all the forces acting on the object are conservative. But we've seen that the work done by a conservative force equals to the negative of change in potential energy. Okay, so we have the following relationship: the negative of change in potential energy equals the change in kinetic energy. Okay, so let's expand this. Change in potential energy is potential energy at the final location. Maybe I should use U. Let me use U. So this would be negative delta U. Okay, so let's try this again. Let's use U for potential energy. So this equals the work done by conservative forces. Okay, so we have the negative of delta U, the change in potential energy, equals the change in kinetic energy. Now let's expand this. This is the negative of potential energy at the final location minus the potential energy at the initial location equals to the difference between the kinetic energy at the final location minus kinetic energy at the initial location. Okay, now let's put the initials on one side and the finals on one side. Okay, so in this case we have a positive initial potential energy, and then we bring this to the other side, it becomes positive kinetic energy initial, and then we take the finals to the other side. This is negative UF. When we take the other side, it becomes the potential energy at the final location. We've got plus kinetic energy at the final location. But remember, this is mechanical energy at the initial location, and this is mechanical energy at the final location. Therefore, this implies mechanical energy initial equals mechanical energy final. Okay, so let's prove it. Okay, so if all the forces acting on an object with non-zero contributions to work are conservative, you can use this principle. You can equate the mechanical energy at the initial location with the mechanical energy at the final location. So what happens is, for example, let's say you're dropping an object. It's falling under the effect of gravity, right? Now when this object falls, of course its kinetic energy increases, goes down, but also the potential energy decreases by the same amount. So if you take the sum of both kinetic energy and potential energy, it remains a constant. Okay, it doesn't change. So the mechanical energy at the top is equal to the mechanical energy just before it touches the ground. So all that takes place is an interchange between potential energy and kinetic energy. But if you take the sum of both forces, it remains a constant. Okay. So let's expand this using the formula of mechanical energy. We know that mechanical energy is half m speed squared plus potential energy, so that this principle can be written as half mass times speed squared plus the potential energy is the initial location, this is initial speed, and then the kinetic energy at the final location plus the potential energy at the final location. Okay, now as you've seen before, the form of the potential energy depends on the type of force. So if the force is gravity, for gravity this formula becomes, for gravity we know that the potential energy is mass times gravity times the y coordinate. Okay, so it will become half m speed squared at the initial location plus the potential, this would be mgyi, mgyi, and that will be half m v final squared plus mgyf. Okay, all right, so this would be the equation for conservation of mechanical energy if the force is gravity. And for the force due to spring, for the force due to spring, we know the potential energy in this case is half times Hooke's constant times extension or compression squared. So the formula becomes the kinetic energy at the initial location plus the elastic potential energy at the initial location equals the sum of the kinetic energy at the final location plus the elastic potential energy at the final location. So this would be the formula to be used if you're dealing with a problem where the force involved is force due to gravity. All right. And of course, if both gravity and spring are involved, if both gravity and spring are involved, the potential energy would be the sum of gravitational potential energy and elastic potential energy, and the formula becomes half m vi squared plus mgyi plus the elastic potential energy, and that equals half m v final squared plus mg, the y coordinate, the final location, plus half k, the compression or extension at the final location. Okay, so if you know if all the forces acting on the system with non-zero contributions to work done are conservative, then you can use these equations to solve the problem. Okay, so let's look at some examples. Let's look at an example. Now, suppose let's say we have a frictionless inclined plane like this. Okay, that's important because friction is not conservative. So we're going to assume frictionless over here. Frictionless. Okay, so suppose let's say the mass of this object is 2 kilograms. Okay, so of course we're going to slide under the influence of gravity, and then we want to find its speed over here. Okay, so the question is calculate its speed at the bottom. All right, first let's see if we can use the principle of conservation of mechanical energy. Now obviously the force that's moving this object is gravity. Okay, so you get this force pulling down, but we have also another force, which is the force exerted by the surface, which is perpendicular to the surface like this. Okay, so this force is not conservative, but you see it's perpendicular to the surface. It's perpendicular to the surface, and so it's perpendicular to the trajectory of the object. So the work done by this force is 0 because the angle between the force, that's the normal force, and the displacement is 90 degrees. So the only force with non-zero contribution to the work done is gravity, and that it follows that the principle of conservation of mechanical energy can be used. Okay, so let's say this over here is 10 meters, and let's say this one is 30 degrees. All right, So the equation would be half m vi squared plus m gyi equals half m v final squared plus m gyf. Okay, so let's put our coordinate system over here. Okay, so this is our initial y coordinate yi, and this is our final y coordinate, which is 0, because I decided to put the origin over here. Okay, and also the initial speed is 0 because it's being released, so you've got vi equals 0. The reason is it's just released. Okay, so we have, according to our coordinate system, the y coordinate, the final location is 0. Okay, and of course we're told the mass is 2 kilograms. All right, okay, and so now we have to calculate this one. This is our y coordinate over here, but we know this is a right angle triangle over here. We know the hypotenuse is 10, and so this one is 10 sine 30. Okay, so we've got yi equals 10 times the sine of 30, or that's 5 meters. Okay, so you can solve the problem now. So this one will go away because it's released. Okay, that's 0, and this is 0, yf is 0. Okay, so you get the following: m gyi equals half m v final squared. Okay, so the mass goes away, so you've got vf squared equals 2 times gravitational acceleration times the y coordinate of the initial location, that is 2 times 10, and the y coordinate of the initial location is 5, so you've got 100. So it follows that the magnitude of the velocity at the final location is the square root of 100, or 10 meters per second, right? Let's look at another example. Suppose we have the following pendulum. Okay, let's say this is a pendulum, and let's say its length is 1 meters. Okay, and let's say it's displaced by an angle of let's say maybe 37 degrees. All right, and then when you let it go, it's going to go back like this, back and forth over here. Okay, it'll go like this. So let's say it's released from this displacement over here. We displace it by 37 degrees, and then we'll let it go. Okay, so the question is calculate the speed over here. We want to calculate the speed at the lowest point. All right, now it's released from rest, so vi is going to be 0 because it's just being released. Okay, and we want to calculate the speed at the lowest point. Okay, let's say the mass is maybe 1 kilogram. Okay, all right, so we're going to use the following coordinate system. Let's put our coordinates, the origin for our coordinate system at the location of the lowest point over here. So you see, this is my initial point, it's my final point. According to this coordinate system, the y coordinate at the final location is 0, because I decided to put my coordinate system right over here. All right, and this would be the y coordinate of the initial location. All right, so let's see how we can calculate yi. You see, this is 1 meters, so this is also 1 meters. Okay, that's the length of the pendulum. Now I can calculate this one. You see, you've got hypotenuse 1 meters, this angle is 37 degrees, you got 90 degrees over here. Okay, so this length over here is 1 minus this one. Okay, minus this. But I can calculate this one. It's 1 times cosine of 37. So you see, we have yi is, you take the whole length 1, and then you subtract this one, which is 1 times cosine of 37 degrees. Okay, cosine of 37 degrees is 0.8, so you've got 1 minus 0.8, that is 0.2 meters. All right, So now we can solve the problem. First, let's establish if we can use the principle of conservation of mechanical energy. What are the forces? We have gravity pulling down on this object, the weight, but also we have the tension in the string pulling up over here. But you see, this tension is always perpendicular to this trajectory, okay? Radius is perpendicular to the trajectory over here. So since the force is perpendicular to the displacement, the work done by this force is 0. It doesn't contribute to the work done. So the only force that contributes to the work done is gravity, and gravity is conservative, so we can use the principle of conservation of mechanical energy. So let's do that. We've got half mass v initial squared plus m g yi equals half m v final squared plus mass times gravity times yf. Okay, so it's being released, so this is going to be 0. The reason is this is being released. Okay, and according to our coordinate system, I put my origin over here, so this one is going to be 0. Okay, yf is 0. So I've got the following equation: mass times gravity times the y coordinate at the initial location equals half m times the speed at the final location. Okay, so you can cancel out the mass, so you get v final squared equals 2 times gravitational acceleration times the y coordinate of the initial location. All right, and that is 2. Gravity is approximately 10, and the value of yi is 0.2. All right, so this is 4. Therefore, the speed is the square root of 4, or 2 meters per second. Right? Now let's look at a roller coaster problem, another example. Suppose, let's say, roller coaster goes like this, and then goes up, and then comes down like this. Okay, so let's say the mass of this object, once again, is, let's say, 2 kilograms. Okay, and then it started with initial speed of let's say maybe 4 meters per second. Okay, so we're going to assume this to be frictionless. We're going to assume frictionless because friction is not conservative. Okay, so let's say this height over here, this height over here is 30 meters. Let's say this height over here is 20 meters. Okay, so the question is, let's call this point A, let's call this point B. So we want to calculate the speed right over here at point B. Okay, so let's put our coordinate system over here. So this is the y equals 0 line over here. Okay, so that means the y coordinate at point A is 30 meters. The y coordinate of point B is 20 meters. Okay, what do we know? The initial speed, or the speed at point A, is 4 meters per second. Okay, and we want to find the speed at point B. Okay, that's the problem. And also we're given mass is 2 kilograms, but we'll cancel out. But anyway, let's write it. Okay, so let's now establish if we can use the principle of conservation of momentum. Let's look at the forces. There are 2 forces acting on this object. One is, of course, gravity pulling down. Okay, there is also the normal force perpendicular to the surface, but the normal force is always perpendicular to the surface, so it doesn't contribute to the work done. It's always perpendicular to the trajectory, right? So the only force with non-zero contribution to the work done is gravity. So that means we can use the principle of conservation of mechanical energy. So our initial point is point A, our final point is point B. So the principle of conservation of mechanical energy can be written as half mass, the speed at A squared, plus mass times gravity times the y coordinate equals half m, speed at B squared, plus m g yb. Okay, so as you can see, the mass cancels out from the whole equation, so we don't have to carry it. Okay, So what do we have? We have half the speed at point A is 4 squared, plus gravity approximately 10, and the y coordinate of point A according to this coordinate system is 30. Okay, that equals half. We don't know the speed at point B, and then we've got gravity approximately 10, and the y coordinate of this location is 20. All right, so we have 4 squared, 16 divided by 2 is 8, and then we have 300 over here. That equals half the speed at point B squared, and this one is 200. Okay, so we've got 308 over here, so it follows that half VB squared equals 108, and so VB squared is 216. Okay, and so the speed is the square root of 216 meters per second. Okay, the speed at point A, that should be 14 point something. Okay, 14, I don't know, 0.5 something. All right, now let's look at problems that have to do with spring. Example, suppose we have a spring over here. Let's say this is the relaxed position of the spring, and let's say its fixed constant is maybe 100 Newton per meter. Okay, so this is the relaxed position, that is no extension, no compression. Suppose we compress it like this. Okay, and let's say we attach maybe a 2 kilogram object. Okay, so we want to find speed just before it leaves the spring. We want to find the speed over here. Okay, and of course the initial speed is going to be 0 because it's just being released. And let's say this distance over here is, let's say, maybe 4 centimeters. Okay, all right, so what do we know? The mass we're told is 2 kilograms. The Hooke's constant of the spring is 100 Newton per meter. Okay, now this is our initial point, this is our final point. Okay, so the initial point, the speed is 0. The reason is just being released. Okay, and the this is the final location, so that's the relaxed position, so xf is going to be 0. Okay, the relaxed position, x is 0, and the initial position that's compressed by 4 centimeters, this compression is going to be -4 times 10 to the power -2 meters. Okay, so the question is to calculate the speed at the relaxed position. Okay, so again we're going to assume frictionless. Okay, so let's establish if we can use the principle of conservation of mechanical energy. So you've got gravity pulling down. Okay, you've got normal force pushing up, but normal force is perpendicular to the surface. It doesn't contribute to the work done. Okay, so the only force in play over here, also there is gravity. Gravity is also perpendicular to the surface, so it's perpendicular displacement. Both normal force and gravity are perpendicular to the displacement, so they don't contribute. The only force in play over here is the force due to a spring. Okay, that's the force that's pushing it this way. So we can use the principle of conservation of mechanical energy, because the only force with non-zero contribution to work done is the force due to spring, and that is conservative. Okay, so let's write that equation. That equation is half mass times initial speed squared, and then plus the elastic potential energy at the initial location equals half m v final squared plus half Hooke's constant times the position at the final point. Okay, so this is our equation. All right, so this would be 0 because VI is 0. Okay, this is just being released. Okay, what else? This XF is a relaxed position, so this will also be 0 because XF is 0. All right, so you got the following question: half K xi squared equals half M VI squared. Okay, so you can see the factor of half goes away, so you've got K xi squared equals M. This is the final, I'm sorry, MB final squared. Okay, so the speed at the final location, the square of the speed, is K over M times the initial compression squared. All right, so that'll be K is 100 is given, M is 2, and this one is 2 times 10 to the power of negative 2. Okay, so you've got this is 50. 5 times 2 is 50 times is 100. 50 times, so it's just basically 1 meters per second. Okay, right. Now let's consider a problem involving both gravity and the spring. Okay, let's consider a problem that involves gravity and spring. Suppose we have this is the relaxed position of a spring. Okay, but then we compress it. Okay, we have this object over here. Let's say maybe its mass is 0.2 kilograms. Okay, so when we let the spring go, what's going to happen is we're going to push on this one, and we want to see how high it rises. Okay, we want to see how high it rises. All right, so let's say our K is maybe 1000 Newton per meter. Okay, and let's say this compression over here, the compression of the spring, let's say it is maybe 4 centimeters. Okay, so if I use this coordinate system over here, okay, so this is my initial point, this is my final point. Okay, so this is my yi, this is my yf. Okay, so the question is, how high will it rise? Okay, so we're looking for this one, yf minus yi. That's the question. So the question is, calculate how high it will rise. Okay, all right, basically we're looking for this difference over here, yf minus yi is we're looking at. Okay, that's the question mark. All right, now you see this object is under the influence of two forces. The spring is pushing up, but also gravity is pulling down. So you've got two forces, and both forces are conservative forces. Okay, so our potential energy is going to be the sum of the gravitational potential energy and the elastic potential energy. Okay, so the principle of conservation of momentum becomes half m vi squared plus mg yi plus the elastic potential energy equals half m v final squared plus mg yf plus half k xf squared. Okay, so we have to use both potential energies for this problem because both the first is the spring and the force of gravity are involved. Okay, so let's write what we know. All right, now this is being released, this location, so the initial speed is 0. Okay, so this is my initial point, this is my final point, so it's just being released, so you've got vi equals 0. Okay, the reason is it's just being released. All right, how about its speed over here? This is the maximum height. At the maximum height, the speed is 0. You see it goes up, its speed decreases, becomes 0, then comes back, okay? So the speed of the final location is also 0. So this is maximum height, that's why it's 0. The turning point, okay? And of course we're given the value of K and the mass. Mass is 2 kilograms and RK is 1000 Newton per meters. Alright, and our goal is to calculate the how high it will rise. Okay, we're looking for this one, YF minus YI. Alright, so let's simplify the equation. Let's put this term to 0 and this term to 0. But also, you see, by the time it's over here, it's not under the influence of the spring. Okay, so at this location, it's not going to have elastic potential energy because it's not under the influence of the elastic force. Okay, so we have also this XF equals 0. Okay, at this point it's not under the influence of the spring. All right, so let's put this terms will go away. The initial speed is 0, the final speed is 0, and there is no elastic potential energy at the final point. Okay, so this equation simplifies to mgyi plus half k xi squared equals mgyf. Okay, mgyf. So it takes the other side. We have mgyf minus mgyi equals half k xi squared. Okay, so the difference in yf and yi, you see, is half k xi squared divided by the weight. Okay, or k xi squared plus twice of mass times gravity. All right, so let's plug the numbers. K is 1000 and xi is 4 centimeters, 10 to the power of -2 squared. Okay, and then divide by the mass is 0.2, and then we've got gravity, that's 10. All right, so you've got, this would be 0.4, we've got 0.4, and we've got 0.04 over here, so it's going to be 10. Okay, no, this is 0.4 and this one is 40. No, this is 4. So 0.4 divided by 4 is 0.1 meters or 10 centimeters. So it's going to rise by a height of 10 centimeters or 0.1 meters. All right. So now we're going to look at non-conservative forces. Non-conservative forces. So we are not, well, these are forces that are conservative. We've seen that conservative forces are the forces for which the work done does not depend on the path followed, and they're also the forces for which the mechanical energy is conserved. So obviously these are forces for which the work done depends on the path followed, and they're forces for which mechanical energy is conserved. Okay, so for this type of forces, work done depends on the path followed, depends on the paths followed, and then of course mechanical energy is not conserved. Mechanical energy is not conserved. Okay, so examples are, these are forces that make an object lose its energy. You can say friction, air resistance, water resistance, and so on. These are forces that make an object lose its mechanical energy. What happens? The energy usually is converted to heat energy or internal energy because of the force of friction. All right. For example, take friction. Let's say you want to take an object from here to here under the influence of force of friction. Now you see, with friction, the greater the distance, the greater the amount of work you have to do, okay? You have to do more work to slide an object along this path than along this path. The greater the distance, the greater the amount of work you have to do, okay? So this is not like conservative forces. The work done actually depends on the path followed to take an object from one point to another, okay? Now, let's look at work done by non-conservative forces. Work done by non-conservative forces. Okay? So I'm going to use work done by non-conservative forces to represent this. And of course, we have already used it WC for work done by conservative forces. Okay, work done by conservative forces. Okay, so now all the forces acting on an object can be classified as conservative and non-conservative, obviously. So you can say that the net work done is equal to the sum of the work done by non-conservative forces and the work done by conservative forces. Okay, this is net work done. Net work done. Okay, but remember the work kinetic energy theorem. Work kinetic energy theorem states that the net work done equals the change in kinetic energy, and we've also seen that the work done by conservative force equals to the negative of change in potential energy. Okay, so let's substitute this. We've got W net equals work done by non-conservative force plus work done by conservative force. So this one is change in kinetic energy, and then we've got, and this is the negative of change in potential energy. Okay, so we see that the work done by non-conservative force is the sum of change in the kinetic energy plus the change in the potential energy, which means this is equal to change in mechanical energy. Okay, so the work done by a non-conservative force is equal to basically to the amount of mechanical energy lost. This is always going to be negative. Okay, so let's take that. So we have WNC equals change in mechanical energy. So in words, that means work done by non-conservative forces is equal to the change, or you can say loss, change or loss of mechanical energy. Mechanical energy. Okay, so let's expand this. So you've got work done by a non-conservative force equals mechanical energy final minus mechanical energy initial. Okay, and we know that this is half mv final squared plus the potential energy at the final location minus half m vi squared plus potential energy at the initial location. Okay, so this is how we calculate the work done by non-conservative non-conservative force. All right. So let's look at an example. Now suppose there's friction involved over here. Okay, suppose we have this object over here. Okay, let's say the mass once again is let's say 2 kilograms. Let's say this distance is 10 meters. Let's say this angle is 30 degrees. Now just let it go. And then suppose we know that the speed at the final location, the final is, let's say, 2 meters per second. Okay, so the question is calculate the work done by friction. Okay, so the effect of the friction would be to slow it down. Okay, so we have friction opposing it, you've got gravity pulling down. Okay, the normal force is perpendicular to the surface, it doesn't contribute anything. So the only two forces are, we've got gravity, which is conservative force, so that's where the gravitational potential energy comes in play, and this force is not conservative. So our non-conservative force is the force of friction between the surface and the object. So the question over here is calculate the work done by friction. The work done by friction. Let's call this A. Okay. So in this case, the non-conservative force is the force of friction. So in this case, the non-conservative force in this case is friction between the surfaces. Okay, between the surfaces. So let's say in this case the work done by the non-conservative force equals the work done by friction. Okay, so we can say that the work done by friction equals half m v final squared plus m gyf minus half m vi squared plus m gyi. Okay, so now let's write what we know. The initial speed is 0 because it's just being released. Okay, so the initial speed is 0. The reason is it's just released. Okay, and if I use this coordinate system over here, okay, so this will be the y coordinate of the initial location, and the y coordinate of the final location will be 0 if I put my origin on the ground axis over here. Okay, so what do we know? So we have bi equals 0, it's just being released, and then yf equals 0 because I decided to put my origin at the ground. This is origin at the ground. Okay, and then we're told the speed at the bottom is 2 meters per second. So you've got v final is 2 meters per second, and also we're told the mass is 2 kilograms. The mass is 2 kilograms. Okay, so now we need to calculate the y coordinate of the initial location. Okay, this is yi, this height over here, but we know this is 10. This is a right angle triangle, this angle 30, so the yi is 10 times the sine of 30. So yi equals 10 times the sine of 30, which is 5. Okay, so vi is 0, this goes away. Yf is 0, this goes away. So we have the following: the work done by friction equals half m v final squared minus mass times gravity times yi. Okay, this is half times 2 we're told the speed is 2 at the bottom, minus the mass 2, gravity approximately 10, and y is 5. Okay, so this equals 4 minus 100. Okay, that is negative 96 joules. Why is it negative? Because friction is opposing the displacement, slowing down. Okay, so this is work done by friction. Now let's say B, calculate the force of friction. B, calculate the force of friction. Okay, we can also calculate the work done by friction a different way. Okay, friction is a constant force, so you can say that the work done by friction equals the force of friction times the distance times of the angle between the force of friction and the displacement. Okay, the distance is 10 meters. Okay, this distance over here is 10 meters, so that's RD. So RD is 10 meters. How about the angle? The angle is 180 degrees. The displacement is this way and friction is this way, so the angle between the displacement and force of friction is 180 degrees. So you've got theta friction equals 180 degrees. So the work done by friction is a force of friction, which we don't know, times 10 times cosine of 180 degrees. Okay, cosine of 180 degrees is -1, so you've got this is -10F. But we just calculated the work of friction over here is -96. This equals -9.6. So the force of friction is 0.96 newtons.